All right, thanks.
So I'll be talking about inherent trade-offs in the fair determination of risk scores. And this is joint work with John and Sandal. So the motivation in the kind of broad framing I want to give this is algorithms are being used a lot to make very consequential decisions, ones that impact a lot of people's lives. And the kind of concern here is that algorithms tend to be optimized for accuracy. That's what we do. But often in real life, accuracy is not the only concern. And so you can imagine that we care about other things, let's say fairness, maybe incentives, public reaction. And so we want to design our algorithms in such a way that we don't, in the search for accuracy, we don't sacrifice these other goals as well. Recently, there's been a lot of work on fairness in machine learning. There's been some work on looking at what happens to word embeddings and how they can be discriminatory in certain ways. And so in this context, I'd like to talk about fairness in risk assessment. Okay, so what is risk assessment? Well, often we need to estimate the probability of a person's future outcome. So you could think that in criminal justice, you might want to know how likely people are to commit crimes. You might want to know how good someone will be at your job, how likely they are to repay your loans, whether someone has cancer, whether someone likes your ad. And the key problem here is that any such tool is going to make some errors. Okay? And what we care about is how these errors get distributed across various groups. And by groups, for this talk, you can think of it as race or gender. And I focus on these specifically because legally these are things that are actually, we have legislation regarding these things, but this kind of applies to any division of the population into groups that you might think of. So I'm going to talk about one particular example, which is in criminal justice. So over summer, many of you may have seen this. There was an article titled, "Machine Bias, There's Software Used Across the Country to Predict Future Criminals, and It's Biased Against Blacks." So the first sentence here is actually true. There is software in our court systems that is used in things like sentencing, parole, and bail decisions. And essentially, there's an algorithm that sees some information about a defendant and outputs a risk score, okay, which corresponds to how likely the algorithm thinks it is that this person will commit crimes in the next few years. Okay, the second part of this sentence is, or the second sentence here is a little less clear. It's biased against blacks, but specifically the analysis was done by ProPublica on a particular tool known as Compass. And this was actually taken to the Wisconsin State Supreme Court. And the Supreme Court ruled that it is okay to use these types of risk tools as long as they're not the only thing that a judge uses in determining, say, a sentence. But here's the condensed view of what ProPublica objected to. So this table here, if we look at this particular number, it's saying of the African Americans who did not go on to reoffend in the future, 45% of them were actually labeled high risk. And so you might ask, well, what is that number for white defendants? And it turns out it's closer to a quarter. Okay, so this seems blatantly discriminatory. And if we look at the other table where people who did go on to commit crimes in the future, what's the discrepancy between predictions for white and black defendants? A similar trend exists, just in the opposite direction. Okay, so this seems wrong. Something is off here. And so the question is, what's going on? And the response by the actuarial risk community, which is academics and practitioners who actually make risk tools like this, they said, this analysis is bad. What we really care about in risk tools is calibration. Okay? Many of you may have seen calibration in the context of the weatherman problem, where the weatherman has to forecast the probability of rain each day, and you need some way of evaluating how good they are at making these predictions. But in the context of risk tools, here's how we're going to define calibration. Given the output of the risk tool, or a risk score, the likelihood of belonging to the positive class, or be committing crimes in the future, is independent of group membership. Okay? And the intuition here is if a judge sees a score, it shouldn't matter what race that defendant is. A score of 0.2 should mean 0.2, regardless of who it is. And when I say a score of 0.2 means 0.2, if we look at my diagram here where I've denoted, let's say group 1 is triangles, group 2 is circles, and then red is positive, green is negative. If you look at the bin labeled 0.2, 20% of the people in that bin are in the positive class. And that applies to 20% of the circles and 20% of the triangles are red. Okay, and this should hold across all bins. And as a side note here, this is actually a weaker version of what's really required by the actuarial risk community, but I'm going to use it as a simplified version, and we'll see it turns out not to really matter. Okay, so the practitioners have said, here's what we really care about. And yet, somehow, the argument raised by ProPublica still stands and still seems like it's something we should do something about, right? Why do we have these different false positive and false negative rates? And so, why do we actually want calibration in our risk tools, right? It turns out that without calibration, things go very wrong. So I'm going to switch to another example really quickly, but this applies to really any model of risk tools you could think about. Let's say I want to hire doctors, but my hiring rule uses scores that are uncalibrated with respect to gender. In the following way, let's say that female doctors with high scores are actually of better true quality than male doctors with those same scores. So what happens? Well, the hospital hires candidates with high scores, as it should. But now, as a patient, the rational thing for me to do would actually be to prefer female doctors over male doctors. Right? Why is that the case? Because I know the people who have been hired have high scores. I know that of the people with high scores, the females actually have higher true quality. So without calibration, the problem is the user of these scores has an incentive to prefer one group to another. Okay? So it turns out we really do need calibration in these risk tools. So the natural question now is, well, why don't we just have everything? Right? Why don't we just list all the things that we want and then achieve them? So here are the objectives that we have. We want to treat people in the negative class equally, regardless of what group they come from. We want to treat people in the positive class equally, regardless of what group they come from. But we also want our risk tool to be calibrated. Okay, so 3 natural sounding constraints, pretty innocuous. So when can we have all of these? Well, it turns out there's a couple of, before I go into when we can do this, I need to formalize things a little bit more. So I'm going to come up with a model. And it's going to be pretty simple. I have some population. And by some process that's abstracted away, everyone gets boiled down into a single feature vector sigma. So I know some piece of information about everyone. And then I have a risk tool that sees this feature vector sigma and assigns everyone a score. And specifically what I know about each person is that everyone is either in the positive or negative class. Everyone comes from either group 1 or 2, and our results extend to multiple groups, but I'm going to, for simplicity, only use 2. And everyone has a feature vector sigma. And so in designing my risk tool, what I want is a mapping, which I'll allow to be randomized, that creates these discrete bins. It maps each sigma to a bin or a distribution over bins, depending on how randomized I want to be. And each bin is labeled with a score between 0 and 1, which corresponds to my probability estimate that someone in that bin belongs to the positive class. Okay, pretty straightforward. Any questions on the model? Okay, so
you don't know, when you see the samples, you don't know if they're positive or negative, right?
Yeah.
You just see the vector, right?
You see the feature vector sigma, and also what we'll allow is that sigma may or may not include information about group. About group. So I will allow for you actually to tell me, here are all the men and here are all the women. That can be encoded into sigma.
We have like population statistics, right?
Sure, you can know all these things. So we'll even allow for each sigma, you know the fraction of people with that feature vector who belong to the positive class. So you can really have as much information as you want. The only piece of information that you may not have is actually the answer, is this person from the positive or negative class? Okay, so in the context of this model, I'm going to rephrase my objectives a little bit. When I say that people of the negative class should be treated equally, what I mean is that the average score that you give to someone of the negative class should be independent of group. Same thing for the positive class. And now formally my calibration constraint will be, so in each bin B I've labeled it with a score, and that should be exactly the fraction of positive people in that bin. Okay, so if I put someone in a bin labeled 0.2, 20% of the people in that bin should be from the positive class, regardless of what group they're from. Okay, when can we have all these properties? So there's 2 trivial cases when all 3 of these things are achievable. The first is my favorite. You have perfect predictive power. You actually know sigma contains all the information you need to know who's in the positive and negative class. And then it's straightforward. You say, if you're in the positive class, I'll give you a score of 1. If you're in the negative class, I'll give you a score of 0. I have no errors, and my rule is calibrated. Okay, so that's great. If you have perfect information, you can do whatever you want. The other kind of trivial case is if my base rates are equal. And what that means is 50% of the men that I look at and 50% of the women also belong to the positive class. And therefore, I can just label everyone with a score of 50%, and you can verify that this satisfies all of my constraints. And outside of this, you can actually show that you can't do anything. So in any instance where all these three properties that we care about are achievable, we either have perfect prediction or equal base rates. Okay. So this might seem kind of like it's game over. And so I'm going to run through a proof sketch of this, but I first want to frame this result in, I mean, it is a negative result, but I do want to frame it in a somewhat different light. ProPublica, there's been some dialogue back and forth, and after seeing this and a few other papers that came out, they labeled bias as mathematically inevitable. And I want to be a little bit more cautious than that. What it's really saying is that utopia doesn't exist. And so instead of saying we need to achieve all of these things simultaneously, it's really saying we need to trade off between these constraints based on the things that we care about. Okay, and this may depend on your particular application. And so I'm going to run through a proof of why this is the case, and it's actually pretty straightforward. First, I'm going to look at our calibration constraint and see what this implies. So to do so, I'll introduce a little bit of notation. NT is the number of people in group T. Mu T is the number of people in the positive class in group T. Okay? And let's analyze our calibration constraint. For any bin B, the score given to the people in that group should be equal to the expected number of positive class people. That's the calibration constraint. If we sum this constraint over all of our bins, we get that the total score allocated to group T is equal to the number of positive class people in that group, which is mu T. Okay, so now we have an expression for the total score allocated to group T. And to complete this proof, I'm just going to derive another expression for the total score, set these equal to each other, and see what happens. And so to do so, let's look at the other constraints on the false positives and false negatives. Let's say X is the average score for someone of the negative class, Y is the average score for someone of the positive class. And right away, you can see that from these two numbers, well, first of all, they should be the same across groups by the constraints that we've imposed. But from these two numbers, I can get another expression for the total score allocated. Specifically, the total score is just the number of people in the negative class times their average score, plus the number of people in the positive class times their average score. And I'm setting this equal to mu T because from the previous slide, we know that this is the case. Now just moving terms around a little bit, we get a linear relationship between the two. Okay. What does this actually look like? Here's the space of feasible false positive, false negative rates. And I'm calling them false positive, false negative. These are really what X and Y kind of correspond to. And you can see that the set of feasible XY pairs is actually a line if you require these things to be calibrated. And the key point here is, well, these lines clearly intersect at the point 0, 1. Why? Because that's the point at which we make no errors, right? I give a score of 0 to the people of the negative class, and I give a score of 1 to people of the positive class. So that's great. They intersect there. But the point is, these are lines. And if they have different slopes, they only intersect in one point. Okay. And now, what is the slope? The slope is actually directly related to the base rate. And so this exactly gives us our result. Either we have perfect prediction, which is this point here, or the lines have the same slope, which means the base rates are equal. Other than that, there's nothing we can do. Okay. And now, as computer scientists, we might think, what if I just relax things to be approximate? Can I kind of get away with cheating a little bit? And so here are some approximate constraints. I just put multiplicative 1 plus or minus epsilons in front of all my previous constraints. Now what can I do? And it turns out that the same flavor of result holds in an approximate sense. And essentially what this is saying is that if you have approximate versions of all your constraints, you have approximately perfect prediction or approximately equal base rates. Right? And so this result, in a sense, degrades smoothly as we move further and further away from our constraints being exactly true. Okay, so at least we can think about, well, what if I actually happen to be in one of these two cases? What can I do then? And so I'm going to claim that if I have perfect prediction or approximately perfect prediction, things aren't that interesting. All I do is just do whatever is optimal, and I have the best thing I can do, right? So the question is, what happens if my base rates are equal or approximately equal? Because what I told you was that the trivial thing to do, which is just lump everyone together in the same bin, is a valid solution, but isn't necessarily the only valid solution, right? So it turns out that when the base rates are equal, here's what we can say. We can satisfy all three of our fairness properties non-trivially if and only if there exists some assignments such that one favors group 1 and one favors group 2. And more specifically, this occurs because the space of feasible assignments for when you have equal base rates is actually kind of a convex set, and you can take nice linear combinations of things. Okay? The other thing that we know is that if you require your assignment to be integral, or this means non-randomized, so given a given sigma, I have to always output the same bin, or the same number, it's actually NP-complete to do this. And not just to find the best, but actually to find anything non-trivial. And this is through a reduction from subset sum, which leaves open the possibility that there's actually a pseudo-polynomial time algorithm to do this. Yeah?
What if you only need to be close to satisfying these things?
That's a good question. So these are in the hard constraint version. I don't have results for when things are approximate. The reduction will break if you require things to, or if you allow things to be approximate, so it's unclear. Okay, so this is what we know. And I just wanted to highlight a little bit of related work that might be interesting for those of you who are actually considering thinking more about this stuff. Just recently, in kind of simultaneous independent work, people have looked at what happens when you do binary classification and you want this equal false positive rates, equal false negative rates, and equal, they call it a PPV, positive predictive value, which is essentially the fraction of the positive class individuals labeled yes should be the same across groups. This is a form of calibration, and they got a similar flavor of results there. Hart-Price-Cerbero actually did something interesting where, while we required calibration and we said you can't do anything, they went in the direction of, if I just want to equalize my false positive and false negative rates, and I say throw away calibration, what can I do? And it turns out there's a nice easy optimization algorithm. It's a simple LP with only a few variables. And what they note is that this actually corresponds to a particular form of affirmative action. And what these two things in conjunction say is that there exists a trade-off, right, between calibration and this affirmative action. So essentially, if I want my false positives and false negatives to be equal, I have to throw away some amount of calibration. And if I require calibration, then I'm essentially banning this affirmative action from being used. And so depending on your application again, you may make this trade-off in different ways. And before us, there's been a long line of work involving fairness in different settings. And I just wanted to highlight a couple. It's gone through phases. If initially, the focus was on statistical parity, which is saying, if I look at the people who I, let's say, hire for my job, a fraction matching the population proportions should be of group 1 versus group 2. Dwork et al. And kind of similar related work talked about different constraints requiring both individual fairness and group fairness, and seeing what happens when you impose those constraints. And also recently there's been a lot of work on fairness in kind of bandit problems where you're hiring people from different groups and you're learning as you go which ones tend to be of high quality. Okay, so in conclusion, there's a lot of considerations when it comes to fairness, and as we've seen, it really does require making some trade-offs between the various things that we care about. And we may have to resolve these trade-offs in different ways. And the example I'll give you is, if you're thinking about school admission, maybe you're okay with some level of affirmative action because, say, you think that you should give equal opportunities to everyone. But for medical diagnosis, you might think the opposite, that you should really just be giving the most accurate information you can. And if certain medical conditions target one population over another, there's really not much you can do about that. So these are all things to think about when resolving these trade-offs. And again, I just wanted to point out, fairness, although it has been receiving a lot of attention lately, isn't the only concern. And there's tons of other objectives that we might want to keep in mind when we look at optimization in social contexts. All right, thank you.
It seems like from a practical perspective, another important aspect is the choice of feature vector. If that's done by a human, but also there's the possibility of injecting bias in how you...
So there's also a line of work on essentially taking a data set and testing it for how discriminatory it can be. And what we're saying is, independently of that, there's still these limitations. And I totally agree that the process of even generating features in the first place is a huge thing.